Cloud point glycol acts as a shale inhibitor in water-based mud by reducing water activity, limiting free water available for shale interaction, and preventing clay swelling and dispersion, while stabilizing the formation, contributing in controlling fluid loss, and enhancing lubrication to maintain wellbore integrity and drilling efficiency. Even if the glycol does not reach its clouding temperature when in contact with shale and clay formations, it still functions as shale inhibitor by reducing water activity and minimizing free water interaction with shale and clays. To optimize its performance, simulating the temperature range at which the glycol clouds upon contact is essential. Glycol clouding decreases as potassium ion concentration increases or with higher glycol concentrations. To determine the optimal potassium ion and glycol concentrations for effective clouding based on circulation temperature, the SimCloud simulator has been developed. The required inputs for SimCloud include KCl concentration by weight, glycol concentration by volume, and total chloride content in the mud, if sodium chloride other than potassium chloride is present in the mud. Example from seawater in offshore drilling. If sodium chloride is absent, leave the total chloride content text box empty, as the system will automatically calculate the chloride concentration based on the provided potassium chloride input. In this demo, let's enter KCl at 8% by weight, glycol at 4% by volume, and total chloride as 0, since there is no sodium chloride present in the drilling fluid. Okay, let's click on the Run button. The chloride content for 8% KCl is extracted from the KCl brine table at 39,949 milligrams per liter. By reviewing the results section, it can be observed that the glycol is expected to cloud out at a temperature range of 159 degrees Fahrenheit to 184 degrees Fahrenheit, which is equivalent to 71 degrees Celsius to 84 degrees Celsius. Let's move the mouse over the graph displaying the clouding temperature versus KCl concentration. As observed in the graph, the X and Y values, representing chloride content and expected clouding temperature respectively, change dynamically as the cursor moves across the graph. Additionally, the graph title updates to reflect the KCl concentration corresponding to the selected chloride content. Let's gradually move the mouse to get a KCl concentration of 10.04%, which delivers a clouding temperature range of approximately 147 degrees Fahrenheit to 172 degrees Fahrenheit, as shown by the Y value at the top of the graph. Please note that the above simulation is based on the middle cloud point glycol. If using a different grade of glycol, users can perform a clouding test with the same input data, 8% KCl and 4% glycol, to measure the clouding range. For example, if the clouding test result shows a range of 149 to 174 degrees Fahrenheit, which is about 10 degrees Fahrenheit lower than the middle cloud point glycol data maintained in the SimCloud database, users can shift the graph down by entering negative 10 degrees Fahrenheit to align the results with the glycol sample used in the drilling fluid. This adjustment allows for straightforward simulation of the clouding temperature at various potassium chloride and glycol concentrations for the specific glycol sample. Now, let's move the mouse over the graph to determine the clouding temperature when the KCl concentration is reduced to about 5% by weight based on the new glycol, with the clouding temperature displayed above the graph. Alternatively, the user can directly change the potassium chloride concentration in the text box to 5% and rerun the simulation for accurate results. As seen in the results section, the clouding temperature has fallen within the range of 168 to 193 degrees Fahrenheit. Okay, with 5% KCl, the chloride content is 24,538 milligrams per liter. Now, let's increase the chloride concentration to 46,350 milligrams per liter and run the simulation. This would result in a clouding temperature range between 135 degrees Fahrenheit to 160 degrees Fahrenheit. Given the chloride concentration, the presence of sodium chloride in the drilling fluid would be equivalent to the chloride content coming from 5% KCl and 3.5% NaCl. Let's click on Report Viewer to extract the report. Drop down the list box and choose the proper report format in Word, PDF, or Excel and export the report. If potassium sulfite is utilized instead of potassium chloride due to environmental regulations, the potassium sulfite concentration must be converted to its equivalent potassium chloride value before running the SimCloud simulation. Let's assume that potassium sulfite at 6% by weight is used in the drilling fluids. To convert this into potassium chloride, please go to the salt rock section and click on the potassium sulfite brine table. Locate the potassium ion concentration for potassium sulfite at the desired 6% by weight. As shown in the table, the potassium ion concentration from 6% potassium sulfite is 28,230 milligrams per liter. Referring to the KCl salt table, we can see that 28,230 milligrams per liter of potassium ion corresponds to a KCl concentration between 5 to 6% by weight. Now, let's proceed to the salt interpolation. From the drop-down list, select KCl, then choose cation in the search text box. Enter the potassium ion value, 28,230 milligrams per liter in the text box, and click the refresh button. As we can see, the KCl brine at 5.216% by weight provides the same potassium ion concentration as 6% potassium sulfite. Next, let's return to SimCloud. Input the KCl concentration at 5.216%, change the glycol concentration to 5% by volume, and run the simulator. Thank you for your time and attention during this demonstration. I hope it has provided you with valuable insight into this application.